Yeah. All right. Part one, tidal turbines. Here we go. Figuring out the mouse. There we go. So my section on tidal turbines is going to talk about a turbine that I worked on at Race Rocks and another river turbine, some of the engineering challenges, and I'm going to try and show a video clip of one of the surveys from June 2010. So the turbine that I worked on was a 3.5 meter Wells turbine, shown in the picture here, and it was in water that was about 30 meters deep. And the top of the turbine was about 5 meters below the lowest of the low tides. So the turbine has a rim generator and it sits on top of a pedestal like a popsicle stick in the ocean. And the spot where we got a berth for it was at Race Rocks, which is on the south end of Vancouver Island. It's a marine preserve, and one of the goals with that demonstration project was to get the lighthouse that is on the Race Rocks Island off of diesel generators. So the idea is that we could take tidal power, generate electricity, charge a battery bank, and then use less diesel on the island, which reduces the chance of diesel spill and damage to all the marine life in that spot. So the turbine is roughly where the yellow star is on the picture. The turbine itself was deployed on a pontoon barge. So you basically hold the turbine underneath the A-frame, and with a couple of tugboats, you head out to that spot. And you have to time the deployment for a friendly slack in the tides, right? So, here's 2 tide tables showing current speed at Race Rocks. It's a mixed semi-diurnal tide, which is really nice because on occasion, you'll get a pair of slacks really close together, which gives you a longer work window, right? So, I'm not a diver, but I know that trying to do work underwater at any more than 1 knot of current is really, really hard. And so, the top image there shows, on subsequent days, 2 opportunities to get some work done. And then the bottom slide shows plenty of opportunity to generate electricity. So that's the end goal, right? We've got this turbine, we're putting it in the water, but my job as an engineer is to come up with structure that is going to survive through all of the really abusive environment that's in there. When I got hired at Clean Current, one of the senior guys there described it to me as working on tidal turbines is a bit like working on satellites. It's really easy to do work on them when they're in the workshop, and it gets really, really expensive to do work on them after they've been deployed, which is super true, right? Because you're trying to get commercial divers out there with the right timing for the slack. And, I live in Vancouver. It's a ferry ride to get over there. It's a lot of stuff to coordinate. So you kind of want to make sure things are as right as they can be before you go. This picture is one of the big panels. There are 6 panels around the outside of the turbine that essentially like an hourglass duct that help channel and streamline water as it goes past the turbine blades. This particular turbine did not swivel, it did not weather vane to point into the flood, and then swivel 180 to point into the ebb. It was a fixed turbine, and the technology, if you're interested, it's a Wells turbine, so the blade doesn't have any twist to it, which means it's not self-starting. You have to, just like your car, you need a starter motor to get it going, but once it's running, it runs fine. And so that was, you end up with this big duct that helps streamline the flow going past your turbine, past the turbine blades. And that means that you don't need to incorporate the swivel into the pedestal to help point this thing into the current. The duct helps align the flow because on a flood, you might have a heading of 0 degrees, and on the ebb might not be 180 degrees away. It might be 165 degrees or something like that. So that's the technology that goes into the duct. The picture is actually a big vacuum infusion. So there's a foam core and then fiberglass skins top and bottom, and they're basically sucking everything in a plastic bag and then drawing resin through the foam composite sandwich under vacuum. And what that does is it gives you really awesome properties in terms of the ratio of resin to fiber. So in a perfect world, you want saturated fiber without much resin and no air bubbles in there. So that was fun. Pretty big job for that. Some of the smaller jobs are just, retrofits, right? Like, hey, we put this post in. We want to go down there and make an improvement to the cable routing when it goes past these flanges. So, I sit in my office and I have the computer model of the post, and I have a picture of the last time I saw the post. You kind of make a plan for what needs to happen. You're like, okay, yeah, I remember, right? This spot where we're working is below the turbine, so it's reasonably deep, maybe 10 meters off the seabed. So I got to have my plan together for how to get everything down there. And I have to work with commercial divers to be like, okay, you guys haven't seen this before, and I've been staring at it on a computer screen for 2 weeks. How can we come up with a plan to get this done? So there's the stuff that I work on in the office. There's the duct tape, electrician's tape, rope, knots, rubber gloves, all the stuff that commercial divers use to attach this. And then you've got your planned work period. So plan A, we're going to head out there in the morning, get as much done as we can. And if it doesn't work, the next morning we have a plan B, so you're trying to line all this stuff up. And then finally you get out there and you get a diver maybe who is too eager to get off the boat, and he dives in before the slack has really arrived. And he's usually working on surface supply, air, and he's on a scuba bottle. And I'm hoping he can get down there and do an hour and a half of work, maybe an hour and 15 minutes. And he comes back in 40 minutes with an empty tank because he's not used to conserving the oxygen, conserving the air. And then sometimes you get pictures like this, like this doesn't look like my computer model anymore, right? Like it's tricky to send the divers down with instructions, and there's no biofouling on my computer screen. But this is one of the awesome things about race rocks is that the water is reasonably clear most of the time, plenty of current, plenty of nutrients going by, and so you get all this amazing marine life down there. And the commercial divers still manage to make it work. I mean, they love diving when they can see. It's amazing having these big tattooed grizzly guys come up, kind of giddy for having seen a sea lion or a wolf eel living down at the bottom of the pile for the turbine. So this turbine went into that spot at Race Rocks. Like this, it's been in and out a couple of times, but it went in 2008 into that spot. And then that's kind of the last I saw of it for a couple of years. And then it's like, oh, like what does Ken the engineer do? Like while his turbine's in the water? You build other turbines. So this is a turbine that we designed for continuous unidirectional flow, right? So the duct on it is a different shape, and it's meant to, river currents is the like in-stream, run a river, hydrokinetic, all these words apply to this guy. It's smaller. Here's a picture of younger Ken next to the turbine. But this was a turbine, the size was actually chosen to fit the Institute of Ocean Technology's tow tank in Newfoundland. So we built this in Vancouver and then created it and shipped it to Newfoundland. And then the guys in Newfoundland tested it there. which I didn't go on that trip. It would have been a fun trip, but it's NRC facilities are always really cool. If you guys ever get a chance to go on a tour, definitely check it out. So after Newfoundland, it came back, we did some more testing, and then we got a spot for it in Manitoba. So on the Winnipeg River, there was a test site set up there where people could go and test their facilities. And, you know, working outside of Winnipeg by the water is not always warm. But we did manage to get the turbine in and out a couple of times there. And it was, you know, nice to be working with fresh water, but it's some tough work days there. So eventually, the tidal turbine at Race Rocks comes out of the water. Any guesses on what it's going to look like? So this is the part where it's like, oh, who knows what grows faster, bull kelp or bamboo? I think bull kelp. What's bull kelp? I thought I looked that up. It was like 30 centimeters a day. And then bamboo, I think you can measure in kilometers an hour. But I think I have a video I can cut to here. Let me see if I can do this. I'm going to pause this share, go back to basic, and then I'm going to share my screen maybe. Hold tight, hold tight. Come on.
Ken, while you're doing this, how long did it take for that turbine to become this fouled?
This was about 2 years. You guys seeing this? Not yet.
Not yet.
Hang on. Resume share. Sharing.
That's better.
Yeah, here we go. Here we go. We are moving again.
Perfect.
So this was about 2 years. So kind of 2008 to 2010. You know, I think this whole video is 15 minutes long, but so what we're looking at here is a piece of plastic pipe that we would put electronics into for telemetry so that the guys can monitor the performance of the turbine from the comfort of the office. Some electrical connectors. And then this is the turbine itself. And so we did a bunch of research trying to figure out like what kind of coatings, you know, what can we paint the duct with to minimize the amount of biofouling on it. You know, and there's some really cool silicone based, they call them fouling release as opposed to anti-fouling. And it's just like if you have some kind of minimum consistent velocity, barnacles, marine life don't get a chance to start growing. So there are a handful of my colleagues that have dove on the turbine. It's a short dive window if you want to. But a lot of this video footage was done by the guys at Pearson College, who was kind of our home base when we were working there. And so even inside these fiberglass covers, there's just tons and tons of marine growth. We were under the assumption that if there was no sunlight and limited water flow, there wouldn't be any growth in there. But you take the fiberglass covers off and it's just full of everything. Yeah. Yeah. This guy. Back to the PowerPoint. Now I'm going to tweak this. Presenter view. So, did I miss a slide? No. All right, so this is what we took out. You know, on occasion, the guys from Pearson would go down and give the turbine a haircut, but you know, it's a pretty dramatic change there. And, you know, the drawback with all this is that, you know, you're trying hard to convert the kinetic energy of moving water into electricity. But Mother Nature, you know, basically is just like, hey, thanks for the artificial reef. And, you know, barnacles start growing places where things are supposed to be smooth and you know, nice bearing surfaces and things like that. And then back to the engineering world, you know, most of the data you look at says that 316 stainless steel is very good corrosion resistance. But there were a lot of things that we took off the turbine after 2 years that were turning into like really porous or really flaked away stainless. I've got a really cool video here because this picture doesn't really do it justice. Let me see if this will work here. So this is underneath a titanium flat washer on a piece of super duplex stainless steel. The low oxygen environment that's in there really messes with the pH, and you get super acidic conditions that basically dissolve the stainless steel that you paid a lot of money for. Anyway, these make nice paperweights. Yeah. Did you try using? Oh, yeah. When the turbine comes out, sidebar question here. When the turbine comes out of the water, they basically go at it with a pressure washer, like a regular Canadian Tire pressure washer to clean it up. Yeah, it's difficult to do any kind of active work underwater because of the cost associated with it. The short dive window and just the sheer amount of biogrowth on there. It's corrosion of 316 that we talked about. Titanium fasteners and duplex. Titanium is amazing, by the way. If you were making something for long-term subsea, titanium is great. Another super nerdy engineering thing to get excited about is these fatigue failures that we found after we took the turbine out, after the turbine came out the first time. So there are a bunch of radial spokes that hold the hub of the turbine at the center. And those radial spokes basically flutter in the wind like a flag a little bit. They get a little bit of turbulence in the wake of the turbine blades when the turbine blades go by. And then we were surprised to see cracks when we cleaned all the biofouling off. And then you go and visit your local materials expert and they go exploring and they cut your broken part up and polish it and etch it and look at it under the microscope. And you see these super beautiful crack lines and crack propagation beach marks, which is, you know, like that's what you see in, you know, your engineering materials class when you're, you know, 19, 20 years old at Waterloo. And so where is this turbine now? It was in the water, it came out, it went back in the water, it came out. It's in a marine preserve, and so they didn't want to leave it in there. They left the post in there. Any guesses on where it is? It's not far from Toronto. Yeah. It's actually, sorry, go ahead.
Kingston?
Kingston, close, close. It's actually super close to where I grew up. It's about a 10-minute walk from my old house. It's at the museum. It's at the Museum of Science and Tech in Ottawa, which is a bit crazy because it means that I can go to the museum with my nephews and nieces and show them something that I did some work on. I didn't think I was that old yet, but it's pretty cool that it's there, and you can see it on Google Earth. So that is the end of what I have on the tidal turbine. I'm going to answer some questions. All right. Question about sacrificial anodes, and the answer is yes. There were sacrificial anodes for the pile. So, so that post, if I can go to that slide here, this post was connected, like electrically connected to a skid of anodes to protect this post. So this post is regular carbon steel. Without the anodes, it would rust. There is other stuff on the turbine. Let me see a good picture here. That we just go with plastic, right? So plastic, bottom right side, is a really good option if it's strong enough for what you're doing, because it doesn't conduct electricity. It's not going to set up a galvanic couple. It's not going to rust. Some plastics are better at resisting biofouling. Yeah. As far as marine life goes, in terms of marine life getting interacting with the turbine, you know, there is no evidence to show that there's been any whale strikes. You know, the divers that go down there are basically like, hey, you know, the marine life is playing with the divers down there, but they're down there on a slack. You know, there have been other studies that look at fish trying to swim through like a Darius turbine, and it's pretty incredible to see the video of the fish swimming amongst the blades of a turbine, and it's, yeah, the fish are pretty good at avoiding the objects. Turbine and orientation to the current. Okay, let me go to a slide that I can show. The question is, can I explain a bit more about the turbine and the orientation to the current? So let's see if I can do this. I'm going to draw with a pen. So current here flows through this channel, right? Back and forth. But what really happens is that maybe it floods this way and it ebbs this way, right? And so this angle in between the flood and the ebb isn't always 180 degrees, right? So when you put the turbine in the flow of the current, I'm trying to erase all this stuff and go back to my pen. The turbine duct here helps take flow that's coming this way and then straighten it out to go straight through the turbine, and then it can continue on its way. You know, and then flow that's coming the other direction, maybe it's coming from this other angle, and it can straighten out as it goes past the turbine blade and then move on.
Okay, thanks.
One of the really interesting things about this whole project, I mean, the turbine was not huge. It was like a 65 kilowatt turbine. The you know, basically a demonstrator project. What they ended up doing was, I mentioned installing a battery bank. You would charge the batteries. So instead of charging the batteries with the turbine, because the turbine's gone, they charge the batteries with the diesel generator. So they run the diesel for a very short period of time, charge the batteries, and then run off the batteries. And that made a huge difference in the amount of diesel they use. Because then you're just not idling the diesel all the time, right?
Right.
What's the RPM in the turbine?
RPM is variable. I think it's 65. I'm going to make up a number. I'm going to call it 65.
Is there a tidal turbine there now?
There's no tidal turbine at Race Rocks anymore. What is left there right now is the pile. So this post plus the section on top of it. So this section is still there. And the reason they chose to leave it there was that all the marine growth that was on it and on the cable running back to the island, it was going to cause more, it was going to disturb the marine life more by removing it than it would have been to leave it there. Yeah. How are we doing for time?
And if you wouldn't mind commenting on the cost benefit of this whole project, costs and the benefit that was derived, please.
Oh, so when you think about turbines, right? Let me find a picture of them. Is there a good one here? So most of the expense when you're dealing with any kind of stuff like this relates to mobilization, demobilization, and maintenance, right? So, you know, in the Bay of Fundy, there is a test site there where you can go in and put in any size turbine you want. But the cost of installing that turbine and getting it to run there is basically like, hey, we should put the biggest one in that we can to generate the most amount of electricity for the fixed cost of deploying it, right? And so there's no way, for example, that this technology, because of the need for stainless steel and, you know, titanium and offshore deployment vessels, tugboats, commercial divers, all of that stuff is pretty specialized skills and substantially more expensive than, you know, an electrician working on solar panels in a farmer's field. So in Ontario, it's super difficult to compete with solar electricity. But when you look at remote places like, you know, the BC's coast, isolated communities on the shoreline of the ocean somewhere, you know, if they are trucking in fuel and running diesels, right, then it becomes more and more attractive to find an alternative to diesel fuel. And, you know, looking at the scale of things, like if you can harness the energy out of moving water, whether it's wave or hydro, like tidal turbines, there is a ton of water and a ton of energy to be had out there. Unfortunately, the environment is super corrosive and not friendly in terms of work windows. So clean current isn't around anymore. Many other companies that have tried to scale up have gone at it for 5, 10 years. There aren't a lot of big turbines out there anymore, sadly. It's fun stuff though.
So does this mean the future of these turbines are very much in question for the future?
Yeah, I mean, this is, when did I leave Clean Current? They were kind of packing things up in 2014, 2015, after about a 15-year run at trying to get funding and trying to, you know, find willing partners to do demonstration sites. You know, I think there's a company called Open Hydro that still has a turbine on the seafloor of the Bay of Fundy. I think that's where it is. You know, you put it in and it costs a bunch of money, and then something goes wrong and you need a bunch of money to take it out. So I don't know, they might make good dive sites someday, but yeah, as far as energy conversion, they're maybe not good investments, but good engineering challenges.
And
Yeah, the lighthouse does have solar now. Yeah.
there were two questions at the beginning about cleaning marine growth off of the turbines. And the questions were about ultra high water pressure and sheet copper.
So, I mean, I don't know what counts as ultra high water pressure. I think your run of the mill pressure washers from like Canadian Tire or Home Depot will do a couple of thousand PSI. I don't know. Somebody might know more than that, me on that. Yeah. And then as far as copper goes, copper is poisonous. And so, you know, you put it down there and cover everything with copper, but over time that copper leaches into the ocean and it kills everything. If you have the time, maybe you can read up on the copper mines in Britannia Bay in Howe Sound between Vancouver and Squamish, and the effluent from the copper mine basically killed all the marine life in Howe Sound. And it's only just started to come back after, when did they clean up that mine? Maybe 2000, 2004, they started cleaning up the stream running out of the mine. So copper is going away, essentially. Like there may be places that still let you paint your boats with a copper-based anti-fouling paint, but it's probably not Canada. It's probably not the EU. Yeah. So I might feel free to add any more questions to the chat about tidal turbines. I can answer them later. I might move on to the diving suit part of the evening.
Sounds good.
Right. So, evolution of the atmospheric diving suit, ADS, stuff it's used for, equipment, all the things that need to work in order to get you in and out of the water safely, some interesting tools. And then the stuff I'm involved with, like day to day right now, is the building and testing of them. So one of the guys at work found this awesome picture of a suit from 1882, Carmagnole, I think. And there it is next to the current suit that I've been working on. Through the years, there have been a ton of different iterations of hard shell diving suits. So all of these suits have the same principle of having some kind of metal exoskeleton to react to the seawater pressure on the outside of you, and then, you know, you're essentially dry inside this aluminum suit. I don't know, are there any ADS pilots in the audience tonight? Hopefully I don't step in anything. Yeah, so the one I'm working on right now is
actually
called,
used to work with hard suits.
Yeah, I've been with OceanWorks since 2015, but hard suits have been around for a lot longer than I've been working.
Yeah, I'm kind of ancient history with it, so I'm curious where it is now.
Yeah. Let's see. These days, they are mostly used for oil and gas inspections. The guys that I'm working with in China plan on using them for dam inspections. US Navy, Italian Navy is kind of submarine rescue, salvage, marine salvage operations. You know, I like to sort of dumb it down and just be like, any short dive, any short work that is deep is pretty effective to be done by the ADS because you don't have to deal with decompression time. So on the outside of the suit, you have all kinds of equipment. A bunch of this stuff can vary from customer to customer. You know, a pan tilt camera, you know, one customer might choose an Ethernet camera, somebody else is working on something else, or choosing something else for it. But there's always a camera that the guys on the surface can control or see what you're doing. The underwater telephone is a through water communications system. So if you were completely disconnected from the surface, you could still communicate. So there's a transducer and a battery pack that goes with that. You know, lights, sonar. The sonar feed goes to the guys at the surface, so they get to see the sonar image. The grippers in your hands are called manipulators. They're a super interesting design done ages ago, but let you spin, grip, and do all kinds of things, and they don't lock in the closed position even when there's high external pressure outside the suit, which is if you pick up something heavy and you want to drop it for whatever reason, you should be able to let go of it, no problem. The magic of the suit is the oil-filled rotary joints. So these are the essentially slewing bearings that let you articulate the arms and legs, turn your wrists, move your shoulders. And they're oil-filled plastic ball bearings on the inside for corrosion management. The vision dome that you look out of is, let's see, it's probably 30 millimeters thick, like a piece of cast acrylic. And then there's like a Lexan protection dome that goes over top of it. So if you fly forwards into something you didn't see, you're not scratching your pressure boundary, right? You're hitting kind of the bumper that's protecting the acrylic dome. And then the one that's always fun to tell the kids is that you get a jetpack. So you have 4 thrusters connected to your backpack that you control with foot pads, and those let you fly up, down, front, back, and then turn left or right. The cable that goes to the surface from the suit is just a cable. It's no hose. There's no air in it. It is just copper for communications and electricity, and then maybe we're working on one with fiber optic line in it right now. So that tether comes down, it connects to a distribution can, and that kind of spreads power out around the suit to the thrusters, into the suit for communications and things like that. On the back of the suit, there's oxygen storage, there's starboard and port redundant life support systems. And then there's a bunch of buoyancy foam on there too to basically help with the trim of the suit. So in a perfect world, the suit sits generally upright, tilted slightly forward, and is about 5 pounds heavy underwater. So you just shut everything off. You just sort of drift slowly down to the seabed. The oxygen system is a key part of the life support because inside the suit, you're entirely on your own. So the surface the guys on the surface don't have any control over your life support system. So you have a starboard side, port side, everything's identical. High pressure O2 bottles outside the suit that you bleed oxygen into the cabin of the suit at about 1/4 liter a minute from either the starboard side or the port side. And the regulators to reduce the pressure from whatever the bottle pressure is outside to, what's the range inside? I forget what it is. Maybe it's 120 PSI when it goes through the flow control valve. So it could be up to 3,000 PSI outside the suit, 120 PSI going into the cabin. And there's flow control management systems in there to do that. So the regulators are outside. You can see them in this view here. They are, draw them here, pen. So this is the port regulator, the starboard regulator. And I think these were originally just regular diving regulators. And then these guys here are called transfer cylinders. And what they do is they plumb an oil line that is has a piston at the, start again. The transfer cylinder essentially is a piston in it. On one side of the piston is high pressure oxygen, and the other side of the piston is oil. So erase, erase, erase. Come on. Because you don't want 3,000 PSI oxygen accidentally going into your cabin. So this side here is high pressure oxygen. This is a piston with seals on it. And then this side is high pressure oil. And so if there is a leak in this oil line, the piston goes to the end of the travel and it stops moving. and your cabin pressure gauge that reads the high pressure oxygen number will go to 0, and the dive will be aborted based on that loss of oxygen. But that's important so you don't fill the suit up with oxygen. And then there's a low pressure line that comes off the side here of the regulator. And that's the one that goes into the makeup oxygen in the cabin.
Ken, could I interject with a question?
Yes.
You're using the term oxygen, so it is pure oxygen. It's not air.
It's pure oxygen. Yeah. Yeah. And that, you know, what do they call it? Pilot. Like, it's important that it comes as breathing gas, or that it's identified as pilot oxygen, to make sure that it's for sure clean.
Yeah.
So, yeah. So the oxygen comes in through these lines here, and then it gets plumbed up to this guy, which is it's basically a pressure equalizer. I don't know. It's kind of an automatic shutoff valve, so that if the cabin pressure increases a little bit, it will close the valve. And if the cabin pressure drops because you're consuming the oxygen and making CO2, it will open and bleed more oxygen in. And in turn with that, there is the oxygen sensor that gives feedback to the surface, the electronics process all of that information. And then the pilot inside the suit, go back to that here, has access to a couple sets of analog gauges, so that he knows on his starboard side, on his port side, what his low pressure oxygen setting is, what the high pressure value is in the bottles on each side, and also the cabin pressure. It's all information that gets checked kind of every 20 minutes while you're on the dive. What else do you see here? This picture is kind of interesting because you can see there's at the top, there's the big eye that's sticking straight up is the secondary lift point. So if you're in the water and somebody needs to grab something to get you out, that's a pick point that they can use. And that red lever is red latch is something the pilot can actuate to release from a main lifting point if he needs to.
So Ken, presumably there's some sort of scrubber that removes or treats the CO2?
You got it. You got it. So this scrubber sits, it's basically I don't know, it's not really a bucket. Container, sits behind the pilot's lower back bum area, kind of in the seat of the pants, and it's filled with Sodazorb or Divesorb or whatever soft no lime scrubber media you're using. And there's 2 cycles for it. One is the normal, we have power from the surface, all the electricity is working right, and there's an electric blower that circulates air through the system. And if for whatever reason the surface power disappears, there's a battery bank that will drive the oxygen sensors and this fan for another 6 or 8 hours. But then if something still hasn't been resolved, then you can switch to a breathing-based air circulation system. And so the pilot has a mask that they would put on in the diving suit, and it's connected to 2 ports on the scrubber pack. And so then it just changes the airflow regime so that you're breathing CO2-rich air straight into the scrubber media. And then the rest of like what you're inhaling is going to be more oxygen-rich. So this scrubber pack seen on the left side of the screen fits into the, draw it again here. It fits into kind of this zone of the pants of the suit. So going back a bit, right? We talked about the oxygen system, the life support system, the stuff that's on the outside of the suit. The next question might be, how do you get into it? And then how do you get in the water? And so, going back to the red suit, most of the time in the office, the suits live on a suit stand like this, you know, and that gives you a chance to turn the hand crank and, you know, undo the waist ring. There's a clamp ring at the waist, undo that clamp ring, and then turn the hand crank, and it basically pries the upper torso up and away from the lower torso. And then you would climb up the ladder on the front or back of the suit and climb into the pants. And then the next stage is you would cross your arms in front of your chest, and then a friend would lower the upper torso down over top of you until the suit is closed and aligned properly. And then you're inside, right? And then you sit there quite happily with the vision dome off while the rest of the pre-dive work is happening. So that'll be the, you know, checking the communications, making sure everything's all set to go prior to you getting started with your dive. The last thing they do before you start the dive is put the vision dome on. So somebody will climb up the front of the suit stand. So they'll climb up this ladder. It's just like 3 steps or 4 steps. And then they'll put the vision dome over top of the face opening of the torso. And then there's 3 screws that attach that. And then you're basically on your own. You know, you're breathing your own atmosphere in there. It's all you. Yeah. So once all that's done and all the pre-dives have been sorted out, there are 2 options for launching. One is just a simple crane-based launch system with a hand-tethered or a hand-tended umbilical. So you can see here, somebody might have whatever it is, like a HIAD telescopic crane, anything to lift the suit and move it away from the side of the boat. And then you have a couple of guys holding the tether to manage how much of the tether is paid out. And once you're in the water, you know, you can fly around and do whatever you need to do. If you are doing a deeper dive, you might use a cage based tether management system. So this white cage here is a cage that the suit would be docked in, and then that cage would go straight to the bottom of the dive site on guide wires down to a clump weight. And then the tether would go from the surface down to that cage, supported by that guide wire. And then the suit would do an excursion of, I don't know, maybe 90 meters, 80 meters from that cage to go and do whatever the task was at hand. And then at the end of the dive, they would go back into the cage and dock themselves in the cage, and then the cage would get pulled back up to the surface. This is a little bit more elaborate launch system, but super effective for deep dives or dives where there is a current that you need to deal with. So next is a video of some ADS hot stab work. Let's see. Yeah, I'll start the video and then I'll read some questions. How about that? I need to go. Laser pointer. I want to click that link, but I can't right now. Here we go. I'm going to pause.
Ken, what's hot stab?
It's from the oil and gas industry. It's a way that you can stab a hydraulic line into a manifold without having to flush the line. Right, so you'll see a picture of it shortly. Pause. I'm getting close. I'm gonna resume share and I think this video is only 3 minutes long. So one of the interesting things about the suit is that it's, if you want to reach something, you have to train yourself to fly, like to reach with the thrusters, not with your arms, right? Because the aluminum suit doesn't stretch. So if you need to get a little closer to something, it's tempting for new pilots just to like, you know, fight a little bit to try and get a little closer, but you're better off to use the thrusters to back away, reset, and then come back in lined up to do the work. So in that manipulator that he's got, he has controls inside the hand pod where he can lock the gripper, lock the manipulator closed. So that white thing is a hot step. You can see the radial hole in it that would allow flow to go axially in one end of the port and then out radially. Yeah, so inside the hand pod, there's a kind of a thumb wheel that lets you lock the gripper closed. So you can pick something up with one of those grippers, lock the jaws on it, and then take your arm out of the arm of the suit and scratch your nose or make adjustments to the oxygen system and not worry about dropping the object you've got. So the thrusters are controlled with foot pads. So below each of this guy's feet, there's 4 buttons on each foot that control the direction of all 4 thrusters, forwards, reverse, and that lets you manage the up, down, front, back. All right, questions? I saw one. Depth on the suit. So right now, most of the suits go to 1,200 feet, so 365 meters. I am working on parts that are able to go down to 2,000 feet, so that's like the 610 meter mark. And yeah, it's, I thought I saw questions asking about the pressure inside the suit. And pressure inside the suit is always 1 atmosphere, or slightly less because they draw a vacuum to check that the seals are properly seated. But yeah, regardless of the depth you go, you stay the same inside the suit. So there's no ear popping, nothing like that. Equalizing, that's the word. And your pilot, she can go down and up as fast as they want, as many times as they want. So you go down to 610 meters in 30 minutes, and you can go back up in 30 minutes after a 6-hour job down there.
How is it different from the suit?
We're obviously better than a nude suit. But these are essentially the same product line as a nude suit. So that's the, yeah.
Can these suits be made robotic, like the new surgical devices there to buy?
Yeah, can they be made robotic is the question. Right now, to my knowledge, at least OceanWorks is not putting a lot of effort into turning the suits robotic, other than, you know, stuff like pilot assist, which is like a auto heading, auto elevation kind of pilot assist feature where you can say, hey, take a heading on the digital compass or the depth sensor and just like manipulate the thrusters to keep that a steady value. in the world of ROVs, so we're talking about robots that are the size of minivans or big SUVs. There's a lot more automation going into those for heavy oil and gas work. So there's some super cool stuff out there. But it's not our jam.
Could you show the photo of suits progressing over time?
I can do that. The photo of the suits progressing over time. There we go. Yeah, so the Newt suit, circa 1986. You know, Glenn would have a much better explanation of the history. You know, at one point, Phil Newton of Newt Suit worked at Ocean Works. It was probably called International Hard Suits back then, maybe. Perhaps Can Dive. Yeah, I don't know the details there. But right now, we're separate companies. So Phil Newton has its own company. He's making a suit called the Exosuit. And Ocean Works is maintaining the old hard suits and working on new ones.
Is there a piston to transduce the pressure scrubber?
The scrubber. The scrubber, is there a piston to move the airflow in the scrubber, I think is the question. The answer is no. It's a regular kind of a squirrel cage blower in there. So the motor here in this portion, just a regular DC electric motor with a circular fan, squirrel cage. Yeah. There is no temperature control inside the suit. And so, you know, if the pilot is diving someplace cold, the pilot would have to dress accordingly and bring food and water in for whatever they need for their dive.
Can it surface by itself?
If the tether breaks, so emergency operations for the suit are actually pretty cool. We only test them in the, you know, sort of as a, we'll call it a factory acceptance test. Sorry. Once every year, once every 5 years, there's a major survey done on all this equipment. And one of the things we have to do is demonstrate emergency surfacing. And so on the top of the suit, there is a cutter, essentially. So right now it's showing as a radial shaft and a spur gear. And connected to that is a knife edge, and you feed the tether through that knife edge. And if you need to, if the tether gets entrapped somewhere, tangled, fouled, the pilot of the suit does have the opportunity to cut that tether. It's not the preferred offshore operation. The best thing to do would have a second asset go down. So whether it's another diving suit that's on standby so that they can clear the fouled tether, or perhaps an ROV to get a second set of eyes down there. But that's, anyway, that would be step one, is cut the fouled tether. And then step two is there's a lever inside the suit. You can kind of see it here. Oh, I lost it. I'm gonna go pen back here. There's a lever that sticks up just here. The pilot can reach around his side or her side and throw that lever. And what that lever does is it releases the thruster assembly. So that releases this entire subsystem on each side of the suit. So if you get into trouble, step one is you cut the tether. Boom, that was expensive. And then step two is you drop one set of thrusters, and then you'll start floating up to the surface. If you want to float faster, you can drop the other set of thrusters. And at that point, you're basically like on a rocket ship to the surface. And again, you don't need to worry about decompression because you're still at 1 atmosphere. So you're going to be at the same pressure in the suit as you would be when you hit the surface.
Bathroom breaks.
bathroom breaks, bio breaks.
That was a question.
Oh, that's a good question. I don't know what the pilots do. Diapers? No coffee that morning?
How do the joints stay flexible with over 500 psi external pressure?
The joints. So I wasn't really going to dive into the details of the rotary joints, but do I have a picture? Yeah, they're a little complicated to explain, but the nuts and bolts of it are that there's oil inside the joint, and the oil inside the joint is acts a bit like a hydrodynamic pressure. The oil pressure is always higher than the pressure outside the suit, so it's proportional to the external ambient pressure. And so it kind of reacts the compressive force of the seawater on the outside and limits the squishing force on the rotary joint. The operator can eat and drink in the suit. So, you know, Camelback, granola bars, there's lots of space in the pants to store snacks. So there's plenty of space in the suit for supplies.
Ken, can you talk a little bit about the applications of this versus a tethered remote vehicle or something like that?
Yeah.
You're not going to go flying around the bottom of the ocean very far with this thing, from what I
No. I mean, this is, you know, if you have a couple of good examples that I have are, you know, there was a job that we were quoting in Australia recently where some work needed to be done on a pipe flange, and the flange was at 160 feet, 158 feet, something like that. And the diving rules in Australia said that anything deeper than 150 feet has to be saturation diving. And so then the cost of bringing a saturation crew in for a short job was super expensive. And so they were looking at bringing in the diving suit to do a small job and do that work. You know, real life applications, you know, I can cut to the tools page at some point, but you know, the guys that are looking at using the suits now want to use it for dam inspection. So they want to see cracks in concrete. They want to be able to pressure wash, you know, basically clean up, inspect. And then you have that judgment call of the pilot down there that has the spatial awareness and the, I don't know, that human feel for how big the space is and what needs to be done. The suit, because of the tether, you know, it's not a good thing to go exploring inside a shipwreck, right? It is a good thing to go down relatively deep, relatively quickly to connect a rescue line or a ventilation line to a disabled submarine. Yeah, but like, you know, if there's a really long job on an oil rig somewhere, definitely a full sat diving crew is just going to be more dexterous underwater getting work done, right? The penalty comes in the decompression time at the end of the job, right? Where you still have all of these people on, like the job is done, but you still need all of the medical team to be around and on standby during the decompression time.
Ken, if you don't mind, just a little bit more about the joints. My understanding is that oils or anything like that, with temperature, they get very viscous. So there must be some sort of a Teflon system rather than an oil system for the rotations. No, could you talk a little bit more about it?
Yeah. So the one of the nice things about seawater is that it's relatively constant, right? Like, you know, you're not going to get plus 30 to minus 30 degrees Celsius temperature swings like you might see in your car, even higher than that for a cell phone that you're leaving on the dashboard of a car. So seawater is what? It's, you guys probably know this better than me, like 2 degrees up to 18, 20, 30 degrees, depending on where your dive is. So it's the temperature swing that the oil needs to function in is actually quite small, which is nice. Then the sealing element inside the rotary joint does run on Teflon, ultra high molecular weight polyethylene.
Right.
Yeah. And so there's a bunch of work that goes into that to qualify the joint. So, when you build a rotary joint, you put it in a pressure pot, you simulate the pressure outside the joint, and you measure the torque it takes to rotate that component. And if the torque is super high, you can take it apart and make adjustments. Or if the oil is leaking out, you can take it apart and make adjustments to find that sweet spot where you're sealing the oil in and getting a workable torque.
Thank you, Ken.
So I've got a couple more slides still, but keep thinking up questions. I saw, when I was in China this past week, I saw some really fun tools. No, 3 weeks ago. And my favorite was the subsea chainsaw. But like the interesting engineering stuff that comes with this is you take a standard hydraulic tool and then you start bolting on adapters to it that make it more user-friendly. So the image on the top left has that arc shape on it. Give me a pen here with the teeth in it. And that's so that you can hang hang that off of a float. And depending on where you hook the float, it changes the angle of the drill bit, right? These handles here are specifically sized for a friendly mate with the jaws of the manipulators so that a pilot can grab this piece and there's a really positive lock onto the end of his arm so that he can use the saw or the drill, or I think this is a jackhammer. This bit of tool, this is the head off of a ratchet wrench. So you go to the Snap-on truck, you buy the wrench, you cut the handle off, and you weld it to a couple of steel plates. And so then the grippers of the suit actually fit into this slot here. And then just the way the manipulator is set up, you can basically start using a ratchet like a socket set in there. And so moving forwards, like some of the small engineering work is like, hey, we've got this specific job coming up. Somebody wants to do an inspection of an aqueduct somewhere. They want to use this sonar. What can we do to make that sonar balanced underwater, or whatever water jet tool they want to use? You can adapt that. One of the things I've spent a lot of time on leading up to this year is redesigning the castings for the suit. So, around 2017, 2018, OceanWorks moved and a lot of the old casting patterns got thrown out. And then, of course, as soon as you throw out the casting patterns, you get a contract to make more castings. So here's the opportunity that you get to say, hey, we had all these old headaches with the old castings. Can you redesign the casting to reduce stress, make it lighter, make it stronger, and make more sensible attachment points for all the stuff? And so just this week, these castings on the top left are being x-rayed for defects. And then they're going to go have all the flashing ground off. They're going to have a dye penetrant inspection done to make sure there are no. So X-ray looks for internal defects. Dye penetrant inspection looks for surface cracks. And then once that's done, they will go to the machine shop and then start to look like the things that you can actually seal water out with. Yeah, spheres are really good for reacting external pressure. They don't really like this picture on the right is where the head of the snowman is connected to the body of the snowman, right? And when you squeeze all of that under external pressure, the weakest point is actually that seam where the neck, like at the neck of the snowman. And so it's pretty nice to have modern engineering tools to predict where the high stress is going to be. And then you can spend a bunch of time in the office massaging your casting shape to come up with something that's going to be light and strong. And then there's all the shiny aluminum parts that come in, and then you get to get your hands dirty, you know, gluing foam together. So this is the inside of one of the rotating limb segments. One of the rotary joints is the blue image on the left. And, you know, the right side is buoyancy foam. So that has a hydraulic crush point of 70, what's the unit there? Yeah, so this is basically super high density closed cell foam to replace the brittle syntactic foam that we're using previously. So you basically buy sheets of 1 1/8 inch thick foam, epoxy the stack together, and then send it to a machine shop to make the backpack shape. The castings are aluminum, by the way. Yeah. So everything on this suit is aluminum, with the exception of some of the through hull penetrations. Those will all be stainless steel. And so then the next thing, once I get all the parts together, is doing the external hydrostatic testing. So you can test individual components, but what the insurance company wants to see, the certifying body wants to see, is once every 5 years, an unmanned external hydrostatic test to 1.4 times the maximum dive depth, right? So that's 750 PSI for this suit. And then once you pass that test with no leaks in the suit, then you put a pilot inside the suit and back into the pressure pot. And then you demonstrate that all of the rotary joints function, that, you know, everything works at pressure, you know, outside your workshop. And so as we move to deeper suit, you have to make sure that your test facility, right, like this test chamber, is suitable for that higher depth. You can do these test dives in open water, but the open water dive is like any other offshore operation, expensive, because you need to have the crew available to get on the boat, deploy, go find a spot that's deep enough, and then do that work. It's much more cost effective to do it in a facility close to the workshop.
Ken, what's the join between the upper and lower half? Is it just plain metal on metal with some sort of clip or screws, or?
Yeah, it is. It's an O-ring face seal. So I don't know how well you can see the test chamber. There's a yellow part and a gray part that come together with kind of a C-clamp around the outside. This zone here, that's the laser pointer. I want a pen. No, I want a pen. Back. Pen. So this zone. So that's just a zoomed in area, but that's the same as what's going to be, you know, around the belt of the diving suit. The difference is that this O-ring is close to the inside wall. So the diving suit is going to look like this, with an O-ring kind of here. And that's one of the O-rings that's, you know, you inspect it before every dive. If there is a hair across this or something like that, you won't be able to draw a vacuum, a gentle vacuum on the suit. when you first close the suit to confirm that all the seals are good. So that's one of the primary seals. And then this clamp ring that goes around the outside here is really just there to hold the pants onto the upper torso when you're lifting the suit. Because as soon as you go underwater, all the external pressure is pushing the two halves of this together, and then this clamp is essentially redundant. Yeah, it's pretty impressive. Like, you can take most of the suit apart with a set of needle nose pliers because everything is like, it's called an Ortman rod. I thought about putting a slide together for this, but I didn't. Super quick. So this might be your leg part. And then we'll put an O-ring groove here. So this side here is 1 atmosphere. And then you have your other part. Let's see if I get this right. It's going to look like this and like this, and maybe have a lead in for an O-ring. And then it goes off to something else. So you have an O-ring in here, and that O-ring will eventually seal on this surface when the two parts come together. And when this annular groove, which is like there's one at the top of the boot, there's one everywhere, lines up here, you can stuff a piece of 1/8 inch diameter Teflon rod, so flexible rod, in this opening. And then what that does is it stops these two parts from separating, right? So now you have this part. Do you guys like my drawing? And then the left-hand part, they can't separate until you pull that rod out. But in order to get that rod out, you just need a pair of needle nose pliers, right? And then out it comes, which is mind-blowing that you can have something that can resist like 750 PSI in the unmanned test that is held together with Teflon rods. But the reason is that when everything's closed up, the load path is through this shoulder into this next part here, right? And the O-ring does the sealing work. So it's Teflon rod is just there to, anyway, sorry, that was a little, I get excited about those. Is there a better picture of them somewhere? You can kind of see in this picture, these openings are the openings where you would feed in that Teflon rod. They're about 1 inch long, maybe 3/8 of an inch deep. And it's just a tiny bit of Teflon that, you know, maybe it's a 18-inch long rod, you stuff it in there. You sharpen the end of it with a pencil sharpener. It's pretty high tech. So I am close to the end. I have a couple of extra slides of nothing especially exciting. But if there are any more questions, fire them my way.
How much does the suit cost?
Suit might cost about $1 million. Really, you should buy 2 of them, because if you've got a contract to do some work and there's a problem with one suit, it's good to have the second one on standby to get that work done. How drones and robotic tech are competing. Yeah, that's probably right. You know, yeah, I'm on the engineering side. There's a whole marketing department that should be looking after that. And so I don't have all those answers. Breathing time on the suit. The suit, when you put the The life support system in the suit is designed around 32 hours of use, right? And so there would be some work time and some rest time. Yeah.
And I'm assuming that these suits are also used for welding and cutting underwater?
Yeah.
Yeah.
Yeah. So any kind of underwater work you want to do, like these guys can, you know, you basically just set up the tooling for the pilot to do the work and then have a crack at it. I think there's a question that says, what is the time for breathing 100% oxygen? And the pilot never gets 100% oxygen. It's always the oxygen, the 100% oxygen bled into the suit is only there to make up the oxygen content that gets consumed by breathing. So the oxygen is always around whatever that magic number is. I think it's 20%, 19. Twist motion to turn 180 using a wrench. Yeah, so inside the hand pod, you can't see them in here very well, but the pilot is working with something with the, you know, the D handle on a snow shovel. It's kind of big enough to put your hand, like your whole hand in, like your fist in, and turn it like a, yeah, like a shovel. Yeah, they're action movies with those tools. Yeah, horror movies. I don't know. Every now and then, I have a friend who's like, "Oh, I think I saw like, you know, either the suit or the rescue submarine in some Hollywood movie." It makes me want to go back now and watch movies like The Abyss. How many suits are in the field? Let's see. We are building suit number 42 and 43 right now. You know, how many suits are currently in use? I don't know. Like, you know, Russia bought 6 suits a dozen years ago, but I don't know how many of them are actively used. So yeah, the number is overall number is still quite low, which makes the supply chain a little bit unhappy sometimes because, you know, anybody we've talked to, they want to make thousands of parts. They don't want to make 2. So the individual pieces are expensive. We are working on incorporating some telemetry systems to help to assist the pilot. I don't know if I would call it AI. There's a question, can we incorporate AI into the suit assist? Right now, it's just feedback from a compass and a pressure transducer, but you know, who knows, in the future that can change, right? Height and weight parameters. So what are the height and weight parameters for the suit occupant? So I'm 6 feet tall, and I can get it in it with a squeeze, right? So there's waist rings. Find a slide for it. Where's a good one? Okay, so in here, pen. Yeah. This one is showing a 2-inch tall waist ring in here. This yellow ring is a 1-inch long arm extension. And then again with the boot. So, you know, with a 6'2" pilot, you can just swap out the 2-inch waist ring for a 4-inch waist ring. If you've got really long arms, you can put spacers in at the wrists. And every pilot will have a, you know, configuration list for like, hey, you know, when I'm in the suit, this is what I like to have it set up at so that I can be comfortable for a 6-hour dive. The training course to be proficient at using the ADS is, I think the courses the guys are running right now are like 3 weeks, 4 weeks. And then what you'll do is you'll alternate days between days on the suit and days with the surface equipment. So like the, you know, on the top side, there's going to be the like all the information that the feedback system in the suit sends to the surface. the guys on the surface can interpret that. And then in the suit, we've taken people that are at the office for show and tell, and you put them in the suit and they go diving in the pool like that day, right? So you don't need any experience to hop in the suit and go for a little zip around. But if you want to be really good at getting a job done quickly, that's time and knowing how to use the equipment that's there. Yeah. So is it time for me to maybe bounce this back to Catherine?
Oh, okay. But one question for you first, Ken. You said you had a couple of extra slides you wanted to show us.
Yeah, all right. I thought this is a clip out of the evolution of the ADS photo. I thought this was interesting because one of the challenges as you get into the detailed design of the suit is matching the weight of the suit with the displacement of the suit, right? So in a perfect world, you want lots of space inside for the pilot to be able to stretch and relax. And you want it to be able to go deep, but that means you need a relatively heavy suit that doesn't displace much water. And then you end up having to add a bunch of buoyancy foam on the outside of it to get to that magic neutral buoyancy zone, plus or minus a couple of pounds. And so it's an interesting challenge, and it's not just for ADS diving suits. It's also for like nuclear submarines, right? Like, there's some kind of golden ratio somewhere where you're like, oh, okay, like, 600 meters is like a practical maximum depth maybe for reasonable materials, right? If you switch from aluminum to steel, you might get a benefit in strength, but then steel is 3 times heavier. And so how do you deal with that in your suit design? You can just make the diameter of the torso a little bit bigger to compensate for that. But the diameter relates to the wall thickness and the strength, which is, anyways, nerdy math problems. I found this slide, these graphs from a promo sheet, and I have no idea how old they are. But if you wanted to see ballpark cost examples, comparing hard suit diving to saturation diving to surface gas, for 2 real world jobs that OceanWorks has done. This gives you like the duration of the job, breakdown into mobilization, actual work, demobilization, and decompression, and the total cost by phase, which is just interesting to see, right? Like it's, saturation diving, you don't, I mean, if you're a diver, you know about it, but, it's hard to get your head around the fact that like, okay, you just did, 3 or 4 days of work on the seabed, and now you need to spend 3.5 days in decompression.
Sorry, Ken, could you move that slide up? Or I don't know whether it's just me, but the bottom part of the example 2 seems to be cut off. Can you move that up a bit?
I can try. I don't think there's a lot else there.
Okay.
Yeah. Screen sharing is paused. Resume share.
Andrew, the titles are the same for the groups of bar charts, are the same as the graph above.
Oh, okay, thank you.
And Ken, we have one other question. What is the weight of the suit at the surface?
I think right now it's 500 kilograms in air. So that's the suit plus the pilot. I'm assuming the pilot is about 170 pounds. And then there's math that you do for like, oh, okay, like the suit came up, but there was a leak in it for whatever reason. So I'm not just lifting the pilot and the suit, I'm lifting the pilot and a pair of pants that are full of water, right? And so there's extra load that goes into that. And then I think my screen share is misbehaving. I'll just go back to this one.
Can this suit be pressurized on the inside in an emergency if you do have a leak?
No, there's there is a pressure relief valve set to 1/3 of a PSI, but that pressure relief valve is the pressure gradient across the suit. So if the pressure inside the suit is 0.33 PSI greater than the pressure outside the suit, then it will crack open and vent. That's really only of any practical use on the surface, but it's a rule that the governing body has in the specifications. But yeah, inside the suit, we do a lot of testing to make sure that there are no leaks, or at least only slow leaks. And if there is a problem, then the dive would be aborted, right? So then you would, you've got a slow leak, you've got like your right foot filling up with water. It's time to fly back to the surface and have a look at which O-ring it is that's causing a problem.
The questions keep coming in.
Yeah.
Where does it develop leaks the most?
Where does it? So there's some interesting history. How much trouble can I get into here? When they first started designing this suit, they didn't have these pretty pictures, computer calculations the same way I have access to these now. So they designed these castings, they machined everything. Come on, resume share. I'm trying to get my screen share to behave again. Give me a second here. Boom. Okay. So when they first made these suits, so like we'll call it the first generation of castings, they put them all together. They did the external pressure test that I talked about with unmanned, nobody in it. And then they took them out, they took them off, and everything was fine. Everything was dry on the inside. But when they went to put everything back together to do a second test, the chin portion of the upper torso had deformed. So that flat surface that we seal the, the flat surface that the vision dome seals against, right? This bottom edge had caved in just a little bit, right? But when the suit was pressurized, like when it was moving, the O-ring was moving with the aluminum and everything stayed sealed. But when you took everything apart, some things sprung back to their flat state and other things stayed in their plastically deformed state. And so they had to go and machine the face of the casting again after that overpressure test. And so knowing that, it's like, oh, okay, when I look at the stress analysis of the suit for this go round, do I see any spots like that where, the chin on the last one would have deformed, and can I solve that problem for the new one? So that was a leak on the first issue, or on one of the early castings. Other common places for leaks are basically like that if you're diving in salt water, you've got an aluminum suit, and if you don't do a good job rinsing the salt water off of the aluminum after your dive, then you end up with corrosion of the aluminum happening. So if your dive crew doesn't do a good job doing the post-dive work, you end up with pitting corrosion on all the suit penetrations. So where the electrical connectors go from the outside of the suit to the inside of the suit, where the oxygen system, copper tubing for that goes through the suit, you end up with corrosion on the upper torso. And so then what you'll find is that at the 5-year maintenance cycle, you'll come back, tear everything apart, do an inspection, and then you'll be like, oh, we need to clean up these sealing surfaces. So you send it to a machine shop and they just skim a little bit of material off until you get a clean surface again. And then you have to come up with the correct adapters to retrofit the old casting to the new, or the old parts to the newly machined casting. Yeah, max dive is 1,200 feet, 365 meters for this flavor. Is it quite cold to leak at those depths? You know, I think those temperature things are kind of interesting, like the temperature in the suit compared to temperature on deck. If you're working at a place where the water is cold, you're going to want to wear a sweater, you know, base layer when you go in. But when you're on deck in the sun, you know, you're going to want some shade. So it's got to be a tricky thing for pilots that are doing dives, someplace where the air is warm, full sun, and the water is colder. Yeah.